Section 1.4 is a kind of a halfway point of chapter 1, right? And that's a good thing because it's where we're going to collect our thoughts and transition from that discussion of atoms and molecules, right? Elements and compounds, physical and chemical changes, to the back half of chapter 1, which is all about math and measurements, okay? And you'll see some slides that are mixed in here that aren't in the text. So if you have any issues with those, make sure to contact me or post on Blackboard for assistance. Section 1.4, which we're covering in this video, is all about measurements. Okay? It says here measurements provide information that's the basis of hypotheses, theories, and laws, which we talked about in the very first video. But they're obviously a huge part of experimentation and observation. Every lab class that you take involves measurements. And in chemistry, and most STEM classes as a whole, right, when you have numbers, measurements, right, they should have 3 pieces of information. And everything in this class should always have all 3. Okay? Size or magnitude, that's the number itself, the value. A standard of comparison, a unit, which is important because just saying 10 doesn't mean anything. Could be 10 milliliters, right? Could be 10 liters. There's a big difference there. And any indication in uncertainty, okay, which we will talk about shortly, getting into that world of significant figures. But before we do that, we need to discuss scientific notation, something that I won't spend a lot of time on because you've all taken a chemistry course in the past, and this has more than likely already been covered. Because in chem, we're always dealing with very small or very large numbers, we frequently use scientific notation, which you may have also learned as exponential notation. You'll just be familiar that the first term when you're writing scientific notation is referred to as the digit term. It's always between 1 and 10. Okay, it cannot be 10 itself. Okay, so between 1.000 and 9.999. The second part of scientific notation is the exponential term, written as 10 with an exponent. And that exponent gives us some information about moving the decimal point. If it's positive, we move the decimal point to the right in our conversion. If it's negative, we move it to the left. And here I have some slides, or one slide with 2 examples where you take numbers and write them from scientific notation into normal notation, and then convert some numbers into scientific notation. That's something that you can try for practice. We'll discuss in the review session, and you can also post on Blackboard to confirm your answers as well. So scientific notation is really the only new thing in the world of numbers. But what about units? Units we'll talk about a little bit longer, okay? Because without units, right, numbers really don't mean anything. Say you are filling a prescription at a pharmacy, right? If you just order 250 something, right, chances are it's 250 milligrams for medication, right? 250 gram pill wouldn't be very comfortable to swallow. In the world of chemistry, we use the SI unit system, which has been around for more than 50 years now. And this is what our SI base units look like, our standard imperial system of units. We have them for 7 different systems, okay? Length, mass, time, temperature, current, amount, and luminous intensity. You can go ahead and ignore electric current and luminous intensity now, right? We won't use them this semester, but the other 5 we will. So know that the SI base unit for length is the meter, represented by M. No mass is a kilogram, represented by the symbol kg. Time in seconds, represented by S. That's an easy one, right? Temperature, that's the one that people mess up the most. Kelvin, represented by a capital K. Notice everything else there was lowercase. Now Kelvin is a capital K. And you need to know amount of substance in moles, represented by the symbol MOL. Okay, and we will explore that more in chapter 3. Keeping in mind that these are just base units, right? Sometimes we have to use a lot of those base units, so multiples, or just part of it, so fractions of those. And we do that by using SI unit prefixes, also known as metric prefixes. And you do have to know these from this and the following slide. These are the ones for fractions, so smaller than the base unit. Okay? Deci, centi, milli, maybe you've heard of those. Okay? Micro, nano, pico, and femto. Okay? Know what those prefixes are, the factor they represent, and the symbol that is used for them. So if I take meters, for example, and I put an N in front of it, I know that means nanometers, something we'll talk about a lot in chapter 6 with wavelengths. We also have multiples, okay, getting bigger, kilo, giga, mega, and tera. Sorry, I said those out of order, kilo, mega, giga, and tera. I don't know, I can't rewind the video when I'm recording live. This is when we're getting larger. Okay? Kilo is the one we'll use most frequently, the factor of 1,000, represented by the symbol K. You've probably heard of kilometers, right? Kilometers, 1,000 meters. So know those metric prefixes, the factor they represent, and the symbol that is used for them that will appear on your first exam. Okay, so let's talk briefly about which each one of those base units means and kind of where they came from. Right, the SI base unit of length is the meter. Okay. Originally came about as 1/10,000,000th of the distance from the North Pole to the equator. You can imagine that's now not exact. Okay, so our new definition is defined as the distance of light travels in a vacuum in that amount of time. Right, that gives us a standard throughout the universe, okay, for light. And a meter's just a little bit longer than a yard. Chances are you've seen a meter stick or a yardstick in your life, so you have a visual medium for what a meter looks like. And this is a handy guide to compare our different units for length. Okay, but we will use meters and the derivatives in this course. We also have mass. A SI unit of mass is the kilogram. Kilogram was originally, where did it first come from? Mass of a liter of water. Well, that wasn't incredibly precise. So the next definition was used on an alloy that's kept in France. And it corresponds to about 2.2 pounds. Now it's actually defined, right? The alloy is still the one that's most commonly known. We've got a picture on the next slide. Okay, but now it's actually defined based on Planck's constant to again give us a constant throughout the world, or sorry, throughout the universe, because other life forms, for example, would not have the same standard. This one that's right here. Okay, so kind of an interesting thought process, the new definitions of these things. How about temperature? Okay, we'll talk about how to convert these things in a later video, but for right now, know that the SI unit for temperature is Kelvin. Notice that I'm not saying degrees Kelvin, right? I say degrees Celsius or degrees Fahrenheit, but it is just called Kelvin, right? The temperature is 300 Kelvin, for example. Okay. There are some situations where we will use degrees Celsius in the SI system. It is allowed depending on the application. We'll talk about that more in chapter 5. Okay. And how does it compare to what we know? Well, okay, a change in 1 degree Celsius is the same as a change in 1 Kelvin. Okay, so if the room warms up by 1 degree Celsius, it also warmed up by 1 Kelvin, right? And about 2.1 degrees Fahrenheit. So they have the same scale, right? They just put their zeros in different places. 0 degrees Celsius is where water freezes. 0 Kelvin is absolute zero. And we'll talk about the conversions later on. Our other unit, time, right? SI unit of time is the second. Piece of cake. We'll frequently use some prefixes with that, like milliseconds, for example. And you will see some applications in chemistry where you're going to use hours, days, and years instead of seconds because it's just more convenient. So we finished section 1.4 with what's known as derived units, because you'll notice when I listed those SI units, we didn't have anything for volume or density, right? We just had things like length and mass. And that's because we can get other units derived from those 7 base units in the SI. We only have the 7 base units from the previous slide. Everything else comes from those, right? So volume, for example, doesn't get a base unit because we can derive a unit directly from it, okay? Thinking about what volume is, length times width times height, right? So if we already have the meter for the standard length, then the derived unit for volume is meter cubed. Okay, just meter times meter times meter. And we frequently see other things used as well, right? Liter, milliliter. Liter corresponds to 1 decimeter cubed, and 1 milliliter is 1 centimeter cubed, also 1 cc. right? You see that in the medical field all the time. I need 10 cc's of whatever, right? 10 cc, cc is cubic centimeter, also milliliter. Just a different standard and a different profession. Here's a nice comparison in the lecture slides for what these meter units look like. And our last one is density. You should know by now that density is mass over volume, right? So if we use our standard SI units for mass and volume, the derived unit for density is kilogram per meter cubed. Right? That's not very convenient to use. So we typically see grams per cubic centimeter or grams per liter for gases. We'll see that in chapter 9. Okay? And of course, grams per milliliter, because that would be the same value for density as grams per cubic centimeter. So from this video, right, know the 7 SI base units, know scientific notation for sure, okay? And know what these units kind of mean, as well as your metric prefixes. That's probably the biggest thing you may have to learn. And then in the next video, we'll talk about the uncertainty part in significant figures.